So very last thing that I would like to do would be okay. Okay.
Andre, actually,
Yes.
can I ask a question to the
Yes.
last lectures? So
Yes, of course.
we were speaking about equivariant cohomology and this
Yes.
equivariant integration, and we had this equivariant parameter you called phi. And one question was that we had to invert it at some point, right? So we had something like equivariant volume of the plane was 2 pi over phi or something like that. And
Yes.
this was because we were integrating one. So my question is kind of why, for example, if we have a given two form, which is closed and invariant, and we do this equivariant extension of it, why do we not have like the equivariant parameter in front of the function we add? And so in this,
we actually have it. We actually have it in front of the function after we make a equivariant extension.
okay, so it is true that we always need to kind of...
Let me answer your question, not with words, but with formula.
Mm-hmm.
Okay?
Mm-hmm.
So thank you very much for asking questions because it is always important. So we studied the following closed form that we wanted to integrate. Okay?
Mm-hmm.
Do you see what's written?
At the moment, it's now it's back to focus. Yes.
Camera is not focused.
Now it's okay.
Okay.
I think.
Now it's okay?
Mm-hmm.
Mm-hmm. Okay. So this form is definitely closed, but this form is not equivariantly closed.
Mm-hmm.
Because this operator acting on omega is definitely RDR that is not zero.
Mm-hmm.
Okay?
Mm-hmm.
So it was an example. I can even consider better example. F of R dr d phi will give us F of R dr. Okay?
Mm-hmm. Mm-hmm.
Then what we can do is that we can construct an equivariantly closed form. I remind the differential equivariant is d plus phi I, in our case, I dr d phi.
Mm-hmm.
So, equivariantly closed form should satisfy condition that omega, that is equivariantly closed, should correspond from two terms, omega 2 plus omega 0. So this is a function, this is a two form. Now, in our particular case, d omega 0 plus phi I d over d phi of omega 2 should be equal to 0. Okay? So we have to solve this equation. I call it equation 1.
Yes, so my question actually arises here already. So why do we not put the equivariant parameter already here in front of omega 0 so that like the total degree of omega equivariant is 2?
Of course. So it is. So when we solve it, of course, we will get that omega equivariant is, of course, would be this plus, if you wish, phi omega 0 tilde. So you propose this. So we have this. In this case, you see that the total, you may call it Gauss number or degree of omega equivariant is 2. 2 comes here from R and phi, and 2 comes here from phi. So this was your question.
Yes, because now, I mean, here we would then, if we would now kind of calculate the integral, right, the equivariant integral of omega equivariant, right, we would just get omega tilde of 0 at the fixed points, like say at 0 and at infinity.
So if we compute equivariant integral of omega equivariant, it would of course be 2 pi over phi omega tilde at the fixed point. And after we cancel here,
so sorry,
we'll get up to pi.
This is cut off, Andrei. This is not visible.
I'm sorry. So that's what I will get.
Yes.
So this case, omega 0 is a Hamiltonian.
Yes, and but almost. It's not. Yes. If you, as Sen proposes, consider equation 1, we may consider. So if what? If omega 2 is a symplectic form, so Sen mentioned important particular case. D over d phi is a Hamiltonian, and it is a Hamiltonian because we know that omega 2 has to be invariant. So what we know? We know that if symplectic form is invariant, it, with respect to the action, then the vector field is Hamiltonian. So in this particular case, this equation is equation to find the Hamiltonian for the vector field. Yes, in this case, it is Hamiltonian. But note that this equivariant extension could be done not only for the 2 form, it could be done in general. But in this particular case, it's really a Hamiltonian. So what we have here is this omega tilde at a point.
So my question is,
now, Donald.
yes, so I understand all this. This is very good. Thank you very much. But then my question is, when we're talking about the equivariant volume, right, we were integrating 1, basically. And we had the problem that we said it's 2 pi over phi, and there was a problem to say, okay, what phi actually is and in which kind of space we're working, because we kind of have to invert phi. But it seems here that actually there should not be this question, because we should not integrate 1, but we should kind of integrate the equivariant parameter somehow. Like,
so no, not integrate the equivariant parameter. So if you talk about volumes, okay, you may also ask what it would be if we actually consider volume measured by omega 2. So we can take equivariant integral of 1, and we will get this. So if we consider, say, the case C, complex plane, we can also do another thing. What else could we integrate? We could integrate some other form that is integrable, and we will see what could come out. In particular, you can consider so-called Distermann-Ekman. Distermann-Ekman. Okay. Distermann-Ekman, yes, integral.
It doesn't come to you.
Okay, so, yes, you see. So you can compute the following thing: omega 2 plus phi omega naught. For general T. Okay? And here you will get the same result. But here the result would be E T phi omega naught at the fixed point.
So the board is cut off.
Already, which cutoff? Okay, I'll do it like this.
Seems that your camera is quite close to the board, it's closer than usual.
Okay, I'll check it. I'll fix it. So you can also compute this. It would still be a localization, but now you have a parameter t here, and you can consider. So I'm sorry. Here we have 2 pi over phi. So here you may consider t equal to 0. So it's an old case. You can consider first order in t. If you consider first order in t, the phi would cancel. And you would see the contribution of this omega 0 at a point.
Okay.
So you can play with this formula in different ways.
Okay, I see. Thank you.
So there are 2 things that I'd like to teach you today. One thing is the interesting setup in physics. I say in physics. It will be the equivariant volume, not of the projective, not only equivariant volume, equivariant cohomology. It's more interesting to study equivariant cohomology, not only of projective space, but also of the maps to projective space. So it will be one thing. Because we will see that this equivariant, that this space is a product of projective spaces. So it's one thing. Another thing, I'd like you to understand why the formula for equivariant volume is as it was written. Namely, last time we ended up maybe I'll start with this first. We ended up last time with the following formula that I wanted you to compute.
So, Andrei, could you check the position of your camera? It's sort of, we are looking at some piece of a of your whiteboard now.
Okay, thank you. I will recheck it. I will do it like this. No, I will do it like this.
It seems that usually the camera is further away, I think. No?
You see, I moved something. So I got this. I don't want to get this. I wanted, so 1 second. I wanted perpendicular.
Mm-hmm.
You see, it's an issue of orientation. The boundary. I got the boundary.
Oh, one of them.
Okay. So I actually want us to understand the following formula that I tried to show last time. And this formula was that if we have CP1 and we had a vector, we had a C star action on CP1. And at least I claimed that the answer was this. Okay? So it was for CP1. And I wanted you to see that here I see actually contribution from 2 points, the North Pole and the South Pole. So here I call this P of sigma. So you may check that it's the correct formula. Okay, I messed with, so up to 2 pi. So I messed with a factor of 2 last time. So here I actually have contribution from 2 points. The question would be how it happens. And another interesting question is, look at this formula. First of all, for phi equals 0, we know this formula, okay?
Sorry, how is this related to the, how the two residues are related to the North and South Pole?
We have 2 points. You may ask how residues are related to this.
Yes.
Okay. Okay. So let us study this formula from 2 possible points of view. So what should we study here? Mm. In the formula, so it's clear that when we compute equivariant volumes, we have two fixed points, right? Because of what? So let me recall. Let me recall how do I get it. So I have CP1 that I understand that C square minus 0 over C star. Okay? Then I have also an action of C star on over CP1. So let me write both actions in homogeneous coordinates. The first action is lambda z0 z1. The second action the second action I can take as follows. Z0 is not changing, Z1 is going to lambda equivariant Z1. Okay? So this I call C star factorization, and this I call C star equivariant. Okay? All together, and I see that C star equivariant has two fixed points. Z0 equal to, okay, first point is Z1 equal to 0. So it's a convenient fixed point. We call it 0 because we used to treat a non-homogeneous coordinate Z. It's a ratio. So that's why this we call 0. And the second is Z0 equals to 0. Clearly, if Z0 equals to 0, then equivariant action coincides with factorization action. So this we call Z equals to 0. And you know how we call this? This we call Z equals to infinity. Okay? So that's how we have 2 points. Now, now we need to compute contributions from these points, right? So my claim, so the claim that I'm going to make is that here we see these 2 points. Maybe you would like, so I'm thinking how to explain that these are contributions from these 2 points in the better way. So you know what I'm planning to do. Let me think for a second. So first thing is that if this polynomial is a constant, we get 0. If this polynomial here is a Fubini-Study form, we get 2 contributions. Okay? So when I say integral around infinity. I'm thinking, I am not ready to tell you now the easiest way to show exactly that these are contributions from these 2 points, while it's always clear that they are these contributions. Let me postpone this question. Okay. The only thing I want you to see is that this formula works. Okay. So let us do it this way. Let us check that this formula works. Okay.
No, it's fine. It's fine. I guess it's just this formula is a little bit obscure in the sense that special values of sigma on the nose don't have anything with special values of z.
Yes, of course. But now let me tell you. So let me still discuss this formula from the following point of view. If you look at this formula, you may see interesting phenomena. And interesting phenomena is that here, that 1 over sigma and 1 over sigma plus phi is something that we already know. 1 over sigma is the equivariant integral of one of these c squared. And 1 over sigma plus phi is an equivariant integral of another c. So actually, what we have in this formula is the equivariant integral of c squared. This one. And factorization by c star actually means this integral over the sigma. So
sorry, I didn't understand this.
Yes, you see, it is a kind of very non-trivial statement. Okay, what I'm going to tell you. I will explain in the following view of this formula.
Okay, I see.
No. Maybe you see, but so
no. At least I see what you're saying. No, I'm.
So equivariant volume of first C that I call 1, it's not a power, is 1 over sigma, where sigma is the factorization. Equivariant volume of the second copy of C is 1 over sigma plus phi. So what we see in this formula, we see here equivariant volume of C squared, that is 1 over sigma plus phi. And then the formula says that we would like to integrate over sigma to get equivariant formula for CP1.
So the C1 and C2, they come with two different U1 action, C star actions, and they are not
Of course, this is action of
standard
C
multiplication.
star factorization.
And this is the product of those.
And this is action of C star factorization together with the C star equivariant.
Right, right, okay.
So C star equivariant doesn't act here,
Yeah.
it acts here. So the strategy to get this formula would be the following. We would like to do the following. We would like to postpone taking this factorization. We would like to study equivariant cohomology here and integrate at the very end. And we should see that that taking factorization over C star actually means taking integral over equivariant parameter. And then we will get this nice formula. So this formula has a meaning and many generalizations. So let us derive this formula first. And let us, to avoid the complication, try to derive it in exactly this particular setting.
So there are two
So when we
equivalent
understand this,
So there are two equivalent parameters, sigma and phi, and then you are getting rid of one of them.
yes.
Mhm.
So the strategy would be to write down equivariant, the strategy would be to write down integral representation for computation of integral over this equivariant product, equivariant CP1. Then, doing some tricks, I will tell you. Integrate out C squared first. And let us predict what will happen. When we will integrate C out, we will get equivariant volume. And then take the second equivariant integration. So this would be a strategy to get this formula. Okay? So let us do it step by step in this simpler setting. Okay? And of course, our trick would be the localization. Okay? So we already, so I will use these notations, okay? This setting. So, first of all, we need to explain how to write down integral over CP1 first, okay? So, to write down integral over CP1, we need to understand that CP1 is, of course, C squared, where we impose equation, this one, and this is called moment map. And then we factorize by U1. So to impose this equation, we of course need, as always, delta function that I'm teaching all the time. So we will need real variable that I will call lambda. I had lambda. Okay, I'll call it L because of Lagrange. And I hope there will be no mixture between lambda that are weights and lambda that are fermions. That is even. And also variable lambda that is odd, okay? So I can just write down the delta function in the following way. So this is the moment map. I'll call it M, okay? Here I put I lambda, and here I put dm. Okay? And I can also make the, if I need, the smearing of the delta function. Okay? So I do this. So in this way, I am writing down the delta function. Now, I need to ask a question. Is this delta function equivariantly closed? So this delta function, this object, is of course E, and here I put dl plus d, and here I put lambda m minus epsilon lambda L. But that's why I know that this object is over dl is of course L d over d lambda. So that's how I see that this object is D-closed. It's dl plus D-closed, and I integrate here. So how can I treat it? So I may ask, is this object closed equivariantly? Okay. So what would you think? Is it closed equivariantly or not?
Well, probably not. You need to add some bits to it to make it closed equivalently.
Yes. So what should I add? And when and where do I see that it is not equivalently closed?
Well, so far somehow U1 didn't enter in the construction in any way. You should I don't know, do Fadeev Popov also. No.
By the way, let us discuss. So in this particular case, we may discuss, is it closed or not closed? Because look, this thing, so I will define Z naught square, it is R naught square. And
This is where we
Z1
cannot see.
square.
We cannot see what you're writing.
Sorry. So Z naught square is R naught square, Z1 square is R1 square. So dm that enters here is horizontal. So maybe here you would agree that it is equivariantly closed. I mean this. It is because the moment map is invariant, of course.
Yes.
So IV applied to dm is, of course, LV of m.
Okay.
It's, of course, 0
Yes.
in general. And that's what we see in formulas. So far, so good. Now, so we make this moment map. Now we would like to divide by U1, okay? And it is here that we may have some peculiarities, okay?
So, and did you require time policing today?
Yes, of course, as always. But I delayed the beginning.
Yes, and what is the anyway? So what is the interval for time policing? I'm not sure.
So how long?
So you are speaking for about 50 minutes now, maybe.
15?
50.
50 already.
Yes.
Oh, I'm going too slow. Speaking about 50, so I'll speak for 10 more minutes and then there'll be a break, okay? Now, how do we factorize with respect to U1? So let me use so-called, so there are two ways to explain this. One way is a mathematical and another way is a physical way. And I'm just hesitating, not knowing what to start with. Okay, let me start with a mathematical way, okay? So suppose there is a manifold X and we would like to understand this integral in terms of integral over x. So it's exactly our case. So mathematical way. And please remind me to tell you the physical way to understanding this. Physical way would be called gauging the fermionic symmetry. So what do I want to get? So here I have projection. And I call it the base. I would like to compute the product of the differential forms, pull back from the base. But if I integrate this over x, I will get, of course, 0. Just because, for example, the degree of this form is higher than degree of x, is lower than degree of x, because they are horizontal. I cannot integrate. So in order to integrate, I need to understand how to integrate along the fiber. And in this way, I use the differential form, in this case to be one form, that I call A. This form would help me to integrate along the fiber. If IV, so V is the action of this U1 on A equals 1, then it's exactly what I want. Now what happens if IV applied to A is not 1? It's something. By the way, so what kind of condition on A I would like to impose? Of course, I would like to impose the condition on A that it should be invariant. Everything has to be invariant.
Well, it looks like a connection.
Yes, it is a connection. Exactly, it is a connection form. If it is a canonically normalized connection form, it's just what I need. But for some reason, I would like to work with LV of A equal to 0 and IV of A non-degenerate. In this particular case, I would like to say that I would like to normalize. Okay, let me call it A tilde. And A tilde is unnormalized connection. You may ask, why should we even bother with this unnormalized connection stuff? Why not to use normalized connection and forget about it? And one of the reasons is that I need to put this normalization condition somewhere, because I would like to have exponential understanding of what is going on. So philosophy that I'm saying is the structure that we are writing should be exponential of something that is exact under differential, and all conditions should be there. That's why it would work in many cases. It would work in quantum field theory. It would be uniform. And also, I would be able to make manipulations, you see? Not only, you see, you may ask, what I am doing, I am fighting for a normalized connection. I will need it in further manipulation, you see? So, I need a condition of normalization. And I'll do it in the following way. Let me write you down the formula. So here is this IVA. And I would like to integrate it over some fermion. And I need to call this fermion somehow. I'll call this fermion rho. And also, I'd like to integrate over to bosons, phi and phi bar. To pick up the proper normalization. Traditionally, this boson is called phi bar. I hope I never used rho. Okay, some people call it eta bar. Okay, I'm sorry, I'll call it eta bar. You see, there are many conventions. So, you may ask, what I'm doing in such simple problem of writing down connection? I am introducing 3 more fields, okay?
So eta bar is a boson and phi bar are fermions.
Eta bar is a fermion, of course.
Eta bar. Okay.
This one.
Yes.
This one is a fermion.
No, I don't understand. Is the formula correct? Should be the IV there or just A? No, I don't understand.
A.
Okay.
Thank you, Pasha. Not only for time policing, but for, you see, so A is a one form, that's why it's fermionic. This is also fermionic. So A is A mu psi mu, fermionic.
So all new fields are fermions, phi and phi bar are also fermions?
No, of course there are bosons. Because I need to divide over.
Yes.
I need to divide over what? I need to divide over IV of A. So actually, would I take this integral, I will get this. So this is a normalized connection.
Mhm.
And then for future generalization,
So this is Fadeev
you might
Popov
easily see
for odd U1, for odd the algebra.
that would I consider multi-dimensional case? This phi should go together with this vector field V if there are several components. While this phi bar
So and they
would
so
go
this
together.
phi's are super ghosts.
Ah, Pasha. Okay, you spoiled the presentation. You knew it.
No, I'm trying to unwind.
Yes, yes, of course. Of course. But I was trying to explain it for mathematicians. So up to now, mathematicians would be able to see that there is this type of presentation. That in multi-dimensional case would it be not only one U1, but many U1s. K. So K U1s. There will be an index A that goes from 1, etc. to K. And here I will have these vector fields. And I will need to create not a 1 form, but a K form. And the idea how to create a K form is to get this K form using some universal thing. Pick up a 1 form, several 1 forms, multiply with eta bar, and then integrate.
So is it intentional that somewhere it's A and somewhere it's alpha? It should be A everywhere.
Intentionally, it's intentionally, because they mean different things.
Uh-huh.
This formula makes sense because there is an operation EVA, A tilde alpha. And here we have the so-called normalization matrix, NA alpha. I hope that this looks like A, not
But
like
there
alpha.
should be the same amount of alphas as U1s, right? And
You
also the
see,
same amount
when you say the same amount of yes, so we want this rank of N to be maximum.
yes. Okay.
Let me tell you that in quantum field theory, this would be interesting operator, etc. But now we are doing finite dimensional case.
Mhm.
Now, great. We understand these bosons. And you see what stands here. Maybe here is a minus sign. Phi A, NA alpha, phi bar alpha. So when we take integrals of a phi and phi bar here, we get the determinant of M. It is just this normalization that we were looking for.
Mhm.
Actually, let me make a comment for mathematicians. When mathematicians in differential geometry try to understand what connection is, of course they consider unnormalized connection. Okay, remark for mathematicians, okay? Okay, I'll erase this, I'll restore it. A tilde is a connection because connection is an equation for horizontal, for tangent vectors, that I'll call U. So this is a set of equations for parallel transport. You need, of course, a tilde, and you can easily multiply this a tilde by any number. Okay, it is the same. This is a connection. However, there's another thing. A is a connection form if it is a tilde normalized like this. Because different differential forms lead you to connection. And there is a question how to normalize it, how to pick a standard one. And we give a definition of a connection form. It's a connection with this normalization condition, or a bit more complicated in the Lie algebra case. So here I'd like to mention the difference between connection, and connection is the set of invariant horizontal planes in the tangent space. To get this space, you do not need this a tilde to be normalized. Okay? But there is also a condition of normalization that you may put for convenience. So here, for mathematicians, it's a subtlety between the connection and connection form. Okay? Unfortunately, this subtlety is not explained in the literature on differential geometry. People say, look, connection is something that IV of a tilde is 1. It's written in the textbooks. I'd like to separate. Okay, Pasha, was it clear?
Sure, no, that's clear.
Okay. So after I'm making this remark on normalization, now I have the possibility, now when I have this, that's how I put down connection, and that's how I put down normalization. I would like to rearrange it in another way. Okay? I would like to treat this and this as pieces of what? Of a covariant differential. Look, this is already a piece of a covariant differential. So this is phi IV acting on what? On this thing. Now, how can I understand this guy? I can understand, sorry, with the bar. I can understand it as at a bar alpha, d over d phi bar alpha, acting on the same guy. So these two pieces together should be understood and may be understood as follows. Let me write down the differential, that I'll say very total differential. Psi mu dv dx mu plus plus my favorite L, d over d lambda, plus, what else do I have? What else do I need? Plus equivariant piece, plus eta bar d over d phi bar and then I see that the full exponential is the total of something. Hmm? Okay? So physicists are calling these multiplets. So whenever you have factorization with respect to some group, you have this multiplet. Maybe it will be proper to call it Fadeev-Popov multiplet, but I actually don't remember who introduced it first.
Sorry, what is multiplet here?
At least Nekrasov, Shatashvili, Moore call it eta phi, eta bar phi bar multiplet. So I know that Gregory Moore looks through the literature. It is his habit to look through the literature. So, and if he didn't found it before physical literature, it means that maybe it was introduced first in physics. Now, as Pasha knows, I explained this on the mathematical level, okay? No physics up to now, only Pasha wanted me to say that it's physics. Of course it's physics. And physics is here. So of course phi bar, eta bar is a gauge fixing of the odd part of the super group with the generator like this.
So sorry, before the physics, so this d total, so there are two parts there that are the usual equivariant differential, and then there are two other parts.
And let us see what stands here. Here, what stands is lambda m plus epsilon lambda L plus A bar eta bar. So all terms that I wrote down in the exponential are exact with respect to this total differential.
Maybe a twiddle phi bar alpha. Wasn't it?
Let us see. Let us see. Tilde phi bar alpha. Ah, yes. Of course, phi bar alpha. So everything what happens here is a homotopy. And here we already see our good old friend, equivariant differential.
And a bunch of other stuff.
Yes, but this bunch is not that terrible. So actually, what is written here, as I told you, is the getting of the odd part of the supergroup. So last time when I explained to you equivariant differential, I told that phi has a meaning as a Chevalley parameter for the superalgebra. It happens to be even. That's why it stands here.
So can I ask you a silly question?
Sure.
So I thought we were considering U1 action only. So I expect only phi, not phi bar appears. So I feel that we somehow extend those U1 action to C star action. I mean, moving from complex.
You see, wait a moment. You see, I call this phi bar for, let me tell you why. Let me tell you why I call this phi bar. I call this phi bar because of the tradition in the physical literature. It's because this structure appears in N equals 2 super Yang-Mills, where there are phi and phi bar scalars. So actually meaning of phi and phi bar is different. Phi takes values in the Lie algebra. Phi bar takes values in the very different space. I intentionally called it by alpha. It is something. So they are very, very different.
Okay, thank you.
And that's why I made all this stuff about normalization, etc. So from the point of view of gauge fixing, phi is a ghost. Phi bar is anti-ghost, or B-ghost in terms of Fadeev-Popov. Maybe it's better to call it B-ghost because, sorry, anti-ghost and not BV, sorry. So phi is a ghost like C ghosts. And this is like B, okay. Like C ghost. And this is like B ghost. And eta bar is like Lagrange multiplier. So these fields are very well known in gauge fixing. However, what we are gauge fixing now, we are gauge fixing an odd group whose Lie generator is contraction with a vector field. That's why these things are very natural for physicists. So let us see how to understand it. We have Lagrange multiplier, and what we have here. here, what we have here is actually what we call the gauge fixing. You may say, come on, we need to put gauge fixing to 0, right? Right, that's what you say. In bosonic theory, in ordinary theory, we take gauge fixing function and we put it to 0. However, this integral over eta puts it down. And note that in Grassmannian world, the odd function equals to the delta function of itself. So this integral over eta makes you delta function here. You do not need, you even do not have, and you do not can do this smearing of delta function in the odd world. That's how, that's why this is the gauge fixing. And this is Fadeev-Popov ghost trick. Because gauge fixing, you take anything that could be fixed, okay? And you need to normalize it properly. That's what these terms are doing.
Yeah.
So this is from the point of view of gauge theory. From the point of view of taking coset space, you arrange the measure on fibers, taking this eta integral. And here you normalize this measure properly. So that's why, and that's how I explain this formula. I try to explain this formula both in the language of physics and in the language of mathematics. Now, about notations. People met this thing first time in the year, at least physicists met this, in the year 1986, I think, or 87. When Edward Wheaton studied n equals 2 super young Mills, twisted. And there was these letters phi and phi bar. That's why he called these bosonic ghosts with these letters. And since then, he was keeping going and going with this. Maybe Atiyah used it earlier, but I don't remember what was the Atiyah's definitions. But this is what is going on. Okay. Okay, so now, Pasha,
Yes.
now it's time to make a break, but this break would be 10 minutes long, right? So now we will have 10 minutes break.
So, and I'll have to decouple at my 6 a.m. sharp because I need to get some sleep before I teach.
Yes, yes. So how long do we have before this?
Well, it means that in an hour and 15 minutes I'll have to decouple.
Yes, yes. You see, decoupling is to be a good policeman. Good policeman who decouples is a policeman who dies You're doing his duty, okay?
Yes, yes,
The
exactly.
best policeman.
Yes, yes, indeed. All right. Mhm.
Паша, сколько у меня еще времени? Вот,
Наверное, минут 5.
еще осталось. Видите?
По-моему, да. Кажется, да.
Все, спасибо.
Мгм. Наверное, пора к нашим баранам.
Да, yes.
Мгм.
Okay. So I'll continue. So what I'm going to do right now, I will let you to guess the correct trick. Okay, Pasha? Because if somebody will tell you the trick, you will say, oh, it's a trick. You will never remember it. However, if you will guess the trick, you will remember it forever, right?
A trick for what? For what?
Now I want you to make the following trick, okay?
Mhm.
What I explained is the following: is that the full integral that we have here is the integral over x's side L lambda. What else? Phi bar, eta bar, and phi of exponential. So at the moment, I will forget about this p star.
Mhm.
Okay, no, I'll keep them. And here we will have exponential of d total applied to something. Okay? So that's what we have right now.
Mhm.
However, we would like to understand the mysterious formulas that I wrote from the very beginning. You know that they work, and but you don't know how to understand them. What is their meaning?
Which formulas for the equivalent integral?
Yes, for the
over sigma.
for the equivalent integrals.
Mhm.
So we always need to remember what we are doing. It helps.
Mhm.
Our goal was to understand the following formula.
It's not visible what you're writing now. It's cut off.
I see.
Maybe you can turn the camera a little bit.
I don't want to change the camera setting. You see, it's so our goal was to understand this formula. Okay. That's what we have at the moment. So at the moment, we do not know how to treat all differential forms, like p star from the base. But we know how to treat some of them, okay? We know that pi star of Fubini-Studi type form is equivalent in equivariant cohomology to phi, right?
Mhm.
So we will not write the universal formula. We will write the formula. You see, it was a general thing for pi star of omega that are equivalent to polynomials of phi. Okay? And this is not the universal integral. Not all differential forms have this form, are like this, but some are. Okay?
But-
You may call them descendants of one.
No, wait a second. So all closed ones are, right?
On, you see, on so here, so on CPU, on CPM, it's true.
Yes.
On CP2, on CP1, it's true. But you see, I'm trying to treat CP1 in the way that could be generalized to arbitrary case. So it happens that all cohomology on CP1, could be represented by polynomials of phi. It is true for some other spaces, but for some spaces it is not true.
Formula to which we are going is a formula specific to CP1. You didn't write for us formula for, I don't know, even an arbitrary toric variety.
But I want to explain it in a way that it will help you. Okay. Pasha, I agree. So for CP1, these forms could be replaced by polynomials in phi. So for CP1 it's true. Okay. And you may think when it is true in general. So now the strategy would be, so here we have star number one. I wrote it. The strategy would be to put here d tot star number two, such that the integral still would make sense. Okay? And then you can forget about C star number one and study d tot of C star number two. This is a strategy. I want you to find such star number two that we could get such formula. The role of phi is played by sigma. I'm sorry. So this is my methodological failure. I had to rename the fields. But
sorry, but I'm confused because there's also phi in that formula. To which
yeah,
we are going.
so this phi was equivariant.
Yes.
And this phi is the phi for U1 action. So my notations are not good.
I see. Okay.
But main idea is the following.
No,
Would
so
there be?
Andrei, actually, I'm confused because that phi appeared in what we claim to be the piece of equivariant differential, which looked like that old phi of well, the equivariant parameter. There was phi AIVA on the right board, yes.
Yes,
And
but this was because of the U1 group over which we take a coset.
Yes, but so which phi is it?
This one.
Yeah, is it the wrong one or the right one? Is it the equivariant one or the just this bosonic field, or both simultaneously?
This field. So in this presentation, in this very general presentation, this phi was the phi of the group over which we take a coset.
So it means that our CP, so at first there is a U1 action when we represent the CP1 as
Yes.
sphere quotient by the group.
Oh, I see.
And there's another Yuan action, which is another one acting on CP1 by
Yes,
rotation.
but at the moment, I am not putting it in.
Yes, yes. So the phi and the d total is the first one, right? The first one.
So here we have this phi, and this is this diagonal action.
Yes,
Okay.
yes, okay.
You see, I put these indices for further generalization. So let us see.
Okay, I see.
That's what we have. We have integrals of x, psi, phi. So that's what we expect to get. We understand that integrals over x and psi could be equivalent volumes. That's we already studied. This integral over d phi is, of course, the integral that we want to be at the very end, knowing the formulas. The thing that we still need to treat somehow is this. We have a bunch of fields here.
Yes.
L, lambda, phi bar, and eta bar. So we need to find a trick that will throw them all away. So the question is how to guess this star number 2 that would throw this field away altogether. So it is a trick. So everything is on the board. I want you to find this star 2. Not in general case, but in very particular case. So let me write down the piece of differential that contains these fields that we don't need, knowing the correct answer. Eta bar d over d phi bar
Yes.
plus L d over d lambda. So actually, I'm asking you to do very simple thing. Now, let me act not as a physicist, not even as a mathematical physicist, but as a mathematician. We see that in these two systems, eta bar, phi bar, and L lambda, there is no cohomology.
Sure.
So we may take them out by some kind of homotopy.
Okay, can I act on something like lambda phi bar or something?
So let us see. So let us do it by trial and error method. What if we put here lambda?
Does it have correct parity even if okay, let's see.
So if we put here lambda phi bar,
Yeah.
we will get L phi bar.
Yes.
So it would take out bosons, but still
There will be also the term eta lambda, eta bar lambda.
great. So let us see what happens. if we apply it here, we will get eta bar lambda plus L phi bar. And probably we need to have some I here. But when we have it, we are done. It is a good exercise to see how to generalize it for other cases. But at the moment, it's exactly what we need. Right? Just do this.
Does it help us to get the formula that we want with this denominator that we want?
Of course. So first, what we need to put here,
And we want to get this phi, the correct phi, the equivalent phi from someplace.
we want to put this term here with a very huge coefficient, lambda capital. So this is very huge coefficient. So physicists say that these fields become infinitely massive and could be integrated away. Let us check the number of these fields, okay? The number of fields lambda and L is the rank of the group, right? The number of fields, so it is, and the number of fields eta bar and phi bar is also the rank of the group. So in general case, there is the same number of lambdas and phi bars. And it is because they are related. So in some sense, lambda stands for the real part of the C star, and phi bar stands for the imaginary part. So it's not stupid to consider this pairing, okay?
Sorry, I didn't understand this point that you were making about the real and imaginary part.
Okay, just imagine that you are studying not just quotient by C star. Just imagine that you are studying the quotient by C star to the power L, okay? Then you will have some number of these, and some number of this.
Yes,
This number would be equal.
yes.
So it is, so what you have here, it is a kind of a pairing between of A's and alphas. The number of these fields is the same.
Yes.
So it is not that stupid to consider this combination, lambda phi bar, that you, Pasha, proposed. But you propose it in one-dimensional case.
Yes.
I want to say that it is good to do it not only in one-dimensional case, but in any case of C star to the n action.
Mhm. So yeah, so
Okay?
can we see this formula arising with? I mean, we can see how this quadruple of fields goes away, but from the integral, but there's the rest of the integral to be taken, and we
Yes.
need
So
somehow
okay.
somehow the correct phi to right.
Okay. So first, it is not stupid to say that in the case of C star to the K action, there is such a pairing.
Mhm.
It's not that stupid. Okay? You see, my mathematical feeling want to say that since these L's and lambdas and these eta bars and phi bars are not very different,
Mhm.
they all are related to the C star action.
Yeah.
So basically, there is this type of pairing. At least the number is the same. And you may see that not only the number is the same. So this quadruple goes away. Okay?
Yes.
So when this quadruple goes away, we don't have this star at all. And quadruple goes away. So what we are left with? We are left with the integration over c to the power n. In our case, n equals to 2. Is this one. And we know how to do it equivariantly. Because we have equivariant localization formulas.
Wait a second. This is an ordinary integral. This is
Of
not.
course.
So what does it mean? I mean, this integral is equal to infinity.
This integral is not over x and psi.
No, over phi. Let me see.
And so you see, first we have this integral, and then we have an integral over phi.
Yes.
So
So there's a
first-
bosonic, there's a non-saturated, but I mean, there's a constant. It doesn't depend on the bosonic variable, right?
Okay, so let us. But my proposal is to study it term by term. Okay.
No, but so there's something that's written on the board, which is on the nose. It is infinity. Or maybe 0 times infinity.
So there is okay. So 1 second. Okay.
Mhm.
So first of all, I'd like to convince you that with a fixed phi, we can take this integral over x and psi.
Mhm.
Okay.
Okay.
It's one thing. And then we will get, for fixed phi, equivariant integration formula.
Mhm.
So since I already represented these differential forms in terms of polynomials of phi,
I think that
I
there's some
can
sort of
easily integrate here.
there's a constant confusion going on about the meaning of phi. Like, is
Phi
it the one that is it the one above or is it not the one above? Now
No,
you're
it's
switching
not the
back.
one above.
Uh-huh.
So So actually, I had to. So it's my mistake, but I picked notations that are known in the literature. Okay.
Right.
So people, however, in the explanation, I had to do it like this.
No, it's all right. But I thought that when you decided to fix the value of phi, you sort of decided
So
that
when
it's
I'm taking this integral,
okay.
first I fix the value of phi and take integral over x and psi. And then I take the phi integral. Okay? So when I fixed phi in this integral, I will get up to 2 pi's. This thing. Because we already integrated c, so we can similarly integrate c squared. So let us see the meaning of this phi square here. Each power of phi came from the covariant integral over the complex plane. Okay? That's why I have phi square in denominator. I also have these nice polynomials.
Sorry, and I'm not sure what you're doing now. Which formula are you starting with? The formula upstairs or the formula downstairs?
The formula downstairs. So this is in the cloud.
Okay.
I am going from downstairs here, taking the x psi integral. That we already studied. But everything is done equivariantly. So after I excluded with your help this lambda and phi bar and all this, I have left only with this system. But now I need to take this integral first in x and psi, and later on integrate over phi. Okay?
So sorry, I'm a bit lost with the logic here. So I mean, this is sort of a regularized integral where we're switching from the normal integral to the equivariant one. With
So once yes, of course. So we had the normal integral. I spent some time to tell you what star 1 is. Now you guessed the star 2. And of course, we can put the star that was used last time.
Okay, so that's the
Remember.
characterization. So we should add that thing. Okay.
So we wanted star 1, then we add your term and this term.
Okay.
So this is the paradigm. So we eliminate this, replacing it by this.
So I mean, all the integrand disappear except this equivalent parameter.
Yes, all these 4, this quartet disappears.
Okay.
We add this equivariant localization term to compute the integral over x and psi. So you see, now everything disappears. It is possible to take integral over c to the power n if there is nothing in. So first I got rid of lambda L, phi bar and eta bar using Pasha-Yot trick. And then using the trick from the previous lecture, I got rid of x psi integral. So everything but phi goes away. Everything goes away. So we are left with the phi integral. And in the phi integral, we integrate along the line.
Sorry, why?
Why we integrate along the line?
Yes.
Because do you remember the origin of the phi field? Phi field in this construction
Yes.
was the bosonic ghost.
Yes.
So it takes values of the line.
Okay. Yes. Yes. Sure. Yes.
And now we know in all this business how to integrate, how to enter, how to put here external C star action. You see, all this lambda phi bar has nothing to do with this external C star. They just commute with it. So I can easily put here this external C star, right? That I'll do in the form. I need to pick up another letter, A capital. So this stands for phi I is for coset C stars, and sigma I would stand for external. So with this, I know how to integrate psi x system. I am just taking equivariant volume. Of C with respect to this equivariantization with both coset and external parameters. So that's why in this particular system, I put here phi and phi plus sigma. So this is the result of equivariant integral of C1, and this is the result of integral of C2, or I call it C0 and C1. Homogeneous coordinates. So I have these homogeneous coordinates here. And I have these equivariant integrals. So the total result is the following. Integral over d phi, p1 of phi, pn of phi, phi plus sigma. Remember that this phi appeared, as you know, as the Fadeev-Popov-Gost for the odd for the odd symmetry. And of course, it's integrated along the line, along the real line. So here, I am almost there with the only problem.
The contour.
Exactly, Pasha. The integral over R is not defined. I have an actual poles, and I need to know how I go around them. However, I know what was the origin of this. It is because I overrun the pretty well defined integral when I had a moment map by by the tricky integral, like fast oscillating integral. It was L phi bar. So it was really a fast oscillating integral. So would I be more accurate? Okay. I would know how to shift these integrals from the real line. And of course, this is determined by the moment map, as we know. So what should be included and what should not be included is determined by the moment map. That's what we studied from the very beginning when we studied the toric varieties. We said, so now I'll erase this. So I already have this formula, so I can erase it from here. We said, we started by saying that we are studying this thing. But this thing is not defined before we put in the moment map, right? So instead, we went to this. So we put a moment map and then we take the quotient. So we see everything in integral representation. So you see some information about the moment map should be in. We met this also when we studied equivariant localization. Remember that we said that the number of fixed points differs because we consider the cases CP1, C, and C star, okay? So, this is exactly when we see this. This integral, I need to put in the quotient marks, okay? So this is the correct formula, but I need to add which poles are in this contour. And this is consistent with localization because when I use your trick, Pasha, this second star is much bigger than the small star. But the contribution from the small star is this I epsilon that stands here and tells you if I need to include them or not.
Mhm.
So you may predict, or we may predict from the very beginning that the final integral would be a bit ill-defined to include the contribution from the moment map. And that's what we have. So we have this nice formula with this with these quotients that says how to put the contour. So we should not get universal formula because of these peculiarities, and we do not have. But we have almost universal formula. We have a universal formula plus additional prescription, which poles should we include or not. And now I want to say something even better here, okay? That in this way, I explained how to compute everything on toric varieties, right? CPN was just particular case. So from here, you know how to compute things on toric varieties. But you should do better. I explained it to you yesterday, but maybe now you will understand better what I mean, what I meant yesterday in our so-called private seminar. That
Oh, this is
that
a formula.
imagine,
This is
Sorry?
CP1. This is a CP1 formula. This is not CPN, right?
so this is CP1. So now what could be CPN formula?
Mm-hmm.
D phi, because we have only one star. Thank you, Fasha, for holding me on the button. Thank you.
Right.
And of course, polynomials on phi, polynomial and small on phi. So this is CPN equivariant. But I want more, okay? I am very ambitious and I would like to compute even more interesting
Andrei-
formulas.
Andrei, I have a sort of a question.
Yes.
So this the formulas that you're writing is sort of a product of a bunch of cohomology classes and then somehow paired with a whatever canonical class. So it's a Frobenius type fundamental class. So it's a Frobenius type operation, but here we are interpreting it as, well, the product is not deformed, but the integration is deformed.
The product is deformed too.
Is it?
So sorry, sorry. Let me see. Let me see. Of course, the product is deformed. Come on. Let us look at the formula. You see, you see that in the equivariant case, you have the point-wise product over the fixed points. So after you have this integral formula, you can decompose it into Laurent monomials.
Yes.
So when you decompose it into Laurent monomials, you would see that first you have a ring
Oh, this is a question already for CP1, right?
Oh,
and
no,
for
this
Jeff-
is CPM.
But the question stands already for CP1.
Yes.
So are we
Yes.
deforming the products?
Product. Product, of course, product is deformed. The product of equivariant, of course. Product is already deformed. Because you need, so when you are making equivariant continuation, you are adding something.
All right.
You need, okay, Pasha, thank you. So I'm sorry, it's so obvious for me that that I am running over, okay, this important moment.
I'm trying to compare it with the quantum cohomology that we discussed just before.
And it's also a good point. In this case, product is also deformed.
Yes.
But here, let us see why here the product is deformed. Product is deformed because you can take, suppose you take the basic form. So d of this is 0 and IV of this is 0, okay? Then there is a question, how do we get the product? Pasha, you confused me a bit, okay? Because the basic form actually represents an element of equivariant cohomology. Okay? Okay. Then, how do we make a product? We multiply, right? So of course we get, so when we multiply, of course we get again an element of equivariant cohomology. However, we need to interpret the result of this product in terms of some basis. The question is, how do we know the basis? Okay? Okay, Pasha. So you confused me. Let me tell you when did you confuse me? Okay. And I need to think because you put me to a puzzle. Okay. So your puzzle is like this: how to define a product in equivariant cohomology. Okay.
Here, the formulas that you're writing, they look like sort of cyclic products, right?
Okay. Okay, it is good to have puzzles. Okay. And I found the following contradiction. Okay. Yes. In this way, things will be more lively. Consider the Fubini-Studi form. on CP1, where everything is equivalent. Yes, Fubini study is equivalently closed, yes. On CP1. So it represents some class. Yes?
Oh, no, I mean, you need to add something to it, right? You need to add a zero form part.
Yes, yes. So right. So Fubini study form. Yes, you are right. So Fubini study form is closed, but it is not equivalently closed. So I cannot say that I just multiply Fubini study forms. I have to say that Fubini study forms plus something sigma omega 0, that this is closed. And then this addition is proportional to sigma, as Donald said from the very beginning. And moreover, this addition is not canonical. Because when I go from Fubini study here, I could add here sigma times 17. It would also be equivalent continuation.
Yes.
It's one thing. Another thing, when I get Fubini study in this way, I would say that Fubini study is something that corresponds to phi. And here and in this case, I'll get the unique continuation of what Fubini study is, equivalently. Here I'm making continuation. And here there is a canonical representative. When I say that Fubini study is represented by phi, in the second case, I easily see that in this ring, phi square is equivalent to what?
Negative sigma phi or something.
Yes. So here I have kind of deformation of multiplication. However, if I use the past one, I don't know what is the canonical way to continue Fubini study. I could always add sigma times 1 here. But in any case, the ring is like this.
So it's a, continuity property of residues.
Yes. So it would be good and interesting to play here. I don't want to push you too much. So you can see what's going on. I just only want to make one more remark. Pasha,
Yes, yes.
should I put one more idea right now, or I should quit for today?
No, that's good. Well, I'll have to decouple in about 5 minutes.
Okay, so one idea for Pasha's 5 minutes, okay?
But
One
you-
idea in 5 minutes, okay?
Mhm.
And it'll be the end. The idea is, so all this was about projective spaces or toric varieties. Now imagine that I want to have hypersurfaces in toric varieties.
Mhm.
What would this mean? I have equation f capital of x equals to 0 such that c star of f of x, c star action, let me say 1 c star, is some lambda to some power p. So homogeneous functions like and I want to get the integral representation for this. And it turns out that I can do it. Namely, I can add here the complex line shifted by 1. I call it fermions. And I can deform. So let me call here coordinate pi. And I can deform the differential to be like this. And this is called causal differential. And I can write down integral formulas where everything is localizing on zeros of f. And then I take a quotient with respect to c star. And I want to run the full program. And you know what? Everything works similarly. The only thing would be that equivariant weights of equation would come in numerator. So I would get formulas like this. So this is for variables, and here I will get formulas for equations. And formulas for equation for this particular case would be so I will get these numerators coming from equations because they are odd. And I will show you examples of this when? Tomorrow. Okay?
So what
I
are
will
those
explain the
letters?
numerators.
What are those letters there? What is mu?
Mu would be a weight of equation with respect to external equivariant parameters. If we just ignore this, we will have this.
Okay. Okay.
Okay.
All right. Yeah. No, sounds great.
So please wait with this knowledge until tomorrow.
Sounds
Okay.
great. Okay.
So this is. So I hope that I somehow explain this mysterious and remarkable formula.
No, well, that sounds awesome. Well, so far,
Okay.
you, I think you explained the case without the Kazul part.
Yes, without the Kazul part.
Yes.
But I'm going to add ingredients one after another, step by step. It will be possible also to extend it to an abelian case. You will see. But step by step, okay?
Sounds great.
And at the end, you'll be able to understand the Nekrasov's formulas.
Or you will explain the Gerental thing.
I will explain both Gerental and Nekrasov, step by step.
Sounds great.
Okay?
All right. Thank you.
So thank you. Pasha, thank you for holding me on the bottom and for your being policeman.
Right. Yeah. Thank you, Andrei.
Okay, so see you tomorrow.